A plain radio signal carries no information, apart from the fact that the transmitter has been left on. The signal has to be modified in some way to be used to convey information, and there are a number of ways in which this can be done. Two of the most popular methods are to modify the amplitude and the frequency, and these will be familiar from the fronts of the traditional radio, AM and FM, amplitude and frequency modulation. Listeners to AM radio will be aware that it's more susceptible to interference from natural and man-made sources because it's not as sophisticated as FM, which is clear and resilient, and is a more complex and unnatural waveform. AM and FM will be easily recognised because of their widespread use in broadcasting. Here, we're not concerned with music and speech, but just binary ones and zeros. Digital 1 and 0 signals could be sent using AM by just keying the signal on and off. Crude but effective. With FM, one frequency could be used to represent a 1 and the second for a 0. This is also a common method and called frequency shift keying, FSK. We can see this signal jumping between its two frequencies here and recorded below in what is called a waterfall display. FSK is important as it's simple to produce and detect and is referred to in LoRa radio transmissions. But LoRa goes further, and in doing so becomes more complex and even more resilient to background noise. Rather than just use the two frequencies of FSK, it sweeps between the two like this, up and down. Now, there are two parameters that may be changed on both the rising and falling signals. These are the rate at which the sweep changes, call this the sweep rate, and the range over which the sweep could change, call this the bandwidth. There are always compromises in communications, and here there are compromises in both sweep rate and bandwidth. Increasing the bandwidth provides a better quality signal, but bandwidth is at a premium. Everybody is vying for space, and bandwidth is valued and restricted. Engineering involves maximising performance using minimal resources. Bandwidths specified for LoRa are therefore restricted under international agreement to 500 kHz, 250 kHz and 125 kHz, and in Europe further restricted to just 250 kHz and 125 kHz. A slow sweep rate is easy to decode and becomes progressively more difficult the faster the change. Here's another potential trade-off. The faster the sweep rate, the more information can be passed, but the more difficult it is to accurately resolve the signal. The European system uses 6 different sweep rates, or spreading factors as they're referred to. These are referenced by numbers 7 to 12. We've already seen that LoRa devices use a LoRa, which is a protocol where any device can just wake up and transmit, regardless of any other existing conversations. As an alert, a device will start by sending this unique training cycle of 8 up sweeps followed by 2 down sweeps. We can break these sweeps into symbols of equal period. The block of 8 is called the preamble and followed by 2 symbols used for timing, called the synchronizing symbols. Any listening device can clearly recognize this preamble as the beginning of a packet, which alerts its attention. The transmitting device is then time limited by which it must complete the rest of its transmission. All of the data content of the packet is contained in the following symbols. Each symbol contains a discrete frequency step representing 8 bits. The data contained in each sweep is probably best shown using these examples. The details, like all good comedy, is in the timing.